Hello, everybody. I have this floating control here. Let's get that off there. Hope everybody's doing well today. This is a follow-up, if you were here 2 weeks ago, to the LPR live demo that we had. We had a lot of people asking about the Tafel constants and how you find them. So all of you gave us the idea for this demo here that we're going to perform, where we're going to calculate the Tafel constants. So, you can use LPR and polarization resistance, what I'm referring to in case you're new to that. And you can very quickly come up with a polarization resistance through the experiment, and you can calculate what your corrosion rate is going to be. But to do that as accurately as possible, you need to know what the Tafel constants are for your specific system. So first, I want to actually start the experiment because it's going to take it about a half an hour to run before I start talking about just everything I'm going to talk about. So let's go ahead and get that up and going first. This is the Gamry framework right here, and this is where we're going to run our experiment through. It's the Tafel experiment. I already have all the parameters set up here. I'm going to do a little bit of a shorter window, only from negative 0.2 volts to 0.2, and this is versus my open circuit potential. The scan rate is also a little bit quicker than I'd normally do it, but again, I'm trying to keep the experiment under half an hour if we can. Everything else here is our sample period. Our sample area is 1 centimeter squared. I have a sample mass that I'm using. The density and the equivalent weight here for steel is being used. And also have this initial delay of about 60 seconds where we're going to measure our open circuit potential. We're going to need that in order to apply our scan right here, since it's versus EOC that we're looking at. So let's go ahead and get this up and going. The first thing we're going to see is our open circuit potential being measured here, and we're looking pretty good. It is nice and stable. We're hovering just between 505 and 506 millivolts. And actually stopped before the 60 seconds that I set up for it, because it met the stability criteria that I set up in that initial delay. So that's good. We like these things to be stable. You need a stable open circuit to make these measurements. So we could sit here and just watch this curve come to life, be generated, but while it's working, and it's going to take about a half an hour, I want to talk about what it is we're looking at in the Tafel constants. So let's go back to PowerPoint quickly. And what we're talking really quickly, can everybody see all of this up top here? I cannot figure out a way to make this go away. As soon as I hit hide, it shows up. Is that something everybody can see? Is it blocking the top of the screen?
Yeah, we can see what you're doing.
Okay, so at the very top, though, do you see the controls for the Zoom meeting popping up?
No.
Okay, I was wondering about that because they're constantly popping up, but they'll just annoy me instead of everybody else. All right. So basically, they keep on popping up in front of me. Basically, all of this is generated from mixed potential theory. And without going too far into it, the basics are that charge conservation requires that for any electrochemical reaction, you must have a reduction reaction and you must have an oxidation reaction. So you always have to have one of each in any electrochemical process. And both of these reactions have to occur at the same interface, on the same surface. So what you end up seeing happening is that both potentials of two said reactions have to come to a common value. And that's what you see happening here. Here we have our hydrogen standard potential right at 0. And in this case, it's a figure that shows zinc. And here we have its potential. And when we have these two reduction and oxidation reactions taking place on the same surface, we have to come to a common potential. And that's going to be the potential that we see that aligns with the intersection right here. We have potential versus our current density on the x-axis here. So this common potential is the potential that these two reaction will come to, and that's known as E-core, or your open circuit potential, or your mixed potential. So another key fact about mixed potential is that at this mixed potential, you're going to have the I-core, the corrosion current that is observed. So right here, you'll have this corrosion current that's observed at E-core. Now, if you start to perturb the system, then you're going to move away both from E-core and the I-core values. But at an open circuit, you should be observing these values. Unfortunately, I-core cannot be measured directly. So at the end of the day, what we're trying to figure out is what this I-core value is. That's something that can't be measured directly, but we can get it from voltage and current data. I guess one other thing I should state is that this I-core value, it's not zero, but both the cathodic and anodic currents for these reactions, they have to be equal to the same value. If not, you'd have an excess and a buildup of charge on the surface, and you can't have that. So both of those have to be proceeding at the same current. And basically, the Butler-Volmer equation here, hopefully everybody's seen this before, but again, we'll briefly discuss it. It is a relationship that models what is happening between the potential and the current in said mixed potential system. Basically, the current that'll be observed in the system is going to be the sum of the anodic and cathodic currents, and this is going to be equal to this I-core value that we observed at the open circuit potential, and then how it is affected, excuse me, by either the rate of the anodic or cathodic reaction that could be dominating, depending on if you have shifted your potential here away from the open circuit potential. So for the anodic reaction, if you move far positive of EOC, then this term is going to become larger. This term right here on the other side is going to become much smaller. The cathodic reaction, you're going to see a dominant, the anodic reaction is going to dominate the system, and this term right here is going to affect what the observed current is. Conversely, if you have, if you apply more negative potential, then you're going to see this term right here start to dominate, and the rate of the cathodic reaction is going to dominate the system. This term is going to essentially fall to zero, and you're going to have you're going to observe a reduction reaction onto the surface. But what I really wanted to look at are these two values, the beta A and the beta C values right here. So those are important. Those are our Tafel constants. That's what we're looking for in this experiment, and those are essentially the slope that you're going to see these reactions take place in. So I use the term slope because we're going to be looking at a lot of graphs, and you'll key into that being the slope. But basically, those are what's controlling, I guess you could say, the system. The two things are going to be how far away you are from your open circuit potential, and then the slope of that reaction, how quickly it is to proceed. So these are the terms that you can change. The E, the BA, that E is the same as this one, the potential, and then the BC values. But these two guys right here, we can find experimentally the potential value right there. That's whatever you apply into the system. And EOC or E-core, the mixed potential, is going to be a constant value in a specific system. So the two things you can change would be the potential and the Tafel constants in a given system. I'm sorry, I shouldn't say you can change the Tafel constants. The only thing you can change is the potential, but the two things that are going to control the system are really the Tafel constants and how far away you are from the EOC value right here. So if we look at experimental data, which this is an example of perfect experimental data, exactly what you would hope to see or achieve as you run these experiments. then this observed polarization plot right here can be modeled with the Butler-Vollmer equation. And as we come here, I'm going to zoom in on this a little bit so everybody can see it a little bit better as well. You have your anodic slope right here when you have the anodic side of the reaction, and that Tafel slope, this beta value, is the slope, as we can observe right here. For the cathodic branch, which, and actually let me back up, we have this Tafel slope right here. This refers to the term we were looking at right there. And let's move back to that other slide. When you are in a more positive potential than what you have at E core, then you're going to be dominated by the anodic reaction taking place on the surface. And as I said before, this is the term that's going to be dominating our equation, our modeling. And then conversely, if you have a more negative potential down here than you have for the corrosion potential, then you're going to have the cathodic branch, which is going to be dominating the reaction and the observed current. And you have a slope associated with that right here, our Tafel slope for the cathodic branch. And one thing you can note is that you can see that we extrapolated two lines, one from the linear region here of the cathodic branch, another one from the anodic region right here, and those two should cross over right at E core, which is also going to be where we observe the corrosion current. So all of these should be intersecting in this one spot right here. And this is the experimental data we are trying to produce so that we can extrapolate what the slope of this branch is going to be, extrapolate what the slope of this branch is going to be. We're going to take a look and see what our E core value is. We can also look and see what the observed corrosion current is. So if you have fitting software like Gamry has, then you can just select a portion of the data, click a button, and we'll spit out all these values for you. But it's fairly simple, especially if you have good data, to just take a look at what the observed E core value is coming over here, and we're going to draw a line that will then cross the E core value, and then we're going to start from the origin right there and find a line tangent to the anodic branch. And hopefully that'll become apparent why we would do things in that order as we move forward. But basically, this cathodic branch, it's not difficult to get a nice linear region to extrapolate from. The anodic branch is a different story. If you were to give just the anodic branch to somebody and say, you know, draw a straight line through the linear region, you're going to have quite a bit of error. But if you can first extrapolate the cathodic branch, have that cross over our observed E core value, and then start from the origin of there and draw a line tangent to the anodic branch, that's probably a good rule of thumb to get an accurate value for the slope for the anodic Tafel constant. The cathodic Tafel constant's a little bit easier, but we'll see that as we move forward to actual experimental data here. Actually, let's check in on our data really fast and see how our curve is looking so far. Looks pretty good so far. Can't say much more about that. Luckily, we're not seeing big jumps in the data or anything like that. We are, I don't want to say it's linear, but we have a smooth data output here. So those are good observations. I'm going back to the PowerPoint. Let me back this up again. So like I said before, the reason that we decided to do this webinar was because last or 2 weeks ago, we talked about using polarization resistance to come up with a corrosion rate of your sample. And we successfully did that, but when doing it, we came up with this RP value right here. And we used it in the Stern-Geary equation to come up with the I-core value. You can rearrange it simply enough to solve for I-core. But the two values that we did not know were our Tafel constants. It's not crucial that you absolutely know what the Tafel constants are. We have a starting value in our software of about 0.12, which is a good estimate across the board of what they can, what they can be. I think the biggest error you'll observe if you don't know the Tafel constants accurately is probably a factor of 2. So, you're not going to be as accurate as if you knew the constants. But the good thing about the LPR experiment is it's very, very fast. Where we're having to wait a half an hour to gain this data, the polarization resistance we can do in just a few short minutes. So first running this Tafel curve and coming up with what our two Tafel constants are is a good starting point. And then using the polarization resistance technique can be a faster way to increase throughput. Another thing to note is when we performed the LPR experiment, we only did a small perturbation of about 15 millivolts either side of the open circuit potential. By doing that, we just slightly perturbed the system. We didn't cause any lasting effects to the surface. We didn't cause any destruction to them. It's a non-destructive technique. Whereas when we're performing this Tafel experiment, we are going, at least in this case, I'm only going 200 millivolts, but you could go 250 millivolts, 300 millivolts out if you so wished, and that's more than just a small perturbation. As I'm looking at the surface of my steel sample that we're testing, I can see bubbles forming on the surface. We have reactions taking place, and so that's another thing to think about when comparing the two techniques. Is that with this Tafel technique, you are actively modifying the surface, whereas the LPR, it's a minimal, small perturbation that shouldn't really cause any damage or modification to the surface. So just two things to keep in mind when thinking about which technique to use. While we're still waiting for this to finish, I want to take a look at data we've collected in the past. So let me switch over here to our analyst program. And this right here was a potentiodynamic scan that we performed at one of the Penn State corrosion short courses that we've put on every year. Sadly to say, I think this is the first year we haven't had it due to coronavirus. But hopefully next year, very soon, we can go back to Penn State and have the short course. It's done during the summer. If that's something you're interested in, send us an email. We can give you details on that and other courses that are available as well. But one thing to note here is that this full potentiodynamic scan is scanning nearly over 3 full volts. You have these regions here where you have a more active region and you move into more passive regions. Always think these kind of look like a river going off into the distance. And the data you can get from these is more qualitative, but what we're concerned with is the data right here. This is the Tafel region. This region right here obeys Butler-Vollmer. So this is the region we're going to take a look at and try to model. So what I did was I isolated some of that data. And this is from the same data that we were just looking at, but I isolated it to a smaller region. And if we go back to the PowerPoint slide, you can see the similarities to what we're looking at right here. We have our anodic branch at the top, and we have our cathodic branch, and the two are meeting here at E-core. So the first thing I can do is just, I'm going to select the data by selecting a portion of the curve right here. So I'm going to take this portion and I'm going to model all these data points right up to this point. So this is the data that I've gathered that I want to model. Come here to potentiodynamic. I'm going to do a Tafel fit. It gives me some starting parameters and a standing starting parameter for the Tafel constants. Notice 0.12 I mentioned before. And we're going to go ahead and calculate. And here we have our fit. So our fitting software uses the Butler-Vollmer equation and modifies the values of our Tafel constants. Let me copy this into Excel so you can see it better. Hold on. Okay, so everybody can see this. From the fit that we just performed, we have our two Tafel constants here, about 61 millivolts and 180 millivolts. It has a corrosion rate, I-core value of about 340 microamps, and our E-core, our mixed potential, or open circuit potential is right about 500 millivolts. And all of that corresponds to a corrosion rate of about 130 milliinches per year. So that's what our fitting software did here. I was fitting this guy. Let's zoom in a little bit closer. So here's the fit that our software came up with on that. Conversely, I can just draw some lines through here and probably come up with very similar values. So that's what I'm going to go ahead and do. I'm going to grab a line here. Actually, I'm going to zoom in a little bit more first. And that might have been a little too close. That's probably going to work out fine. But the first thing I'm going to do is I'm going to draw a line right here relative to our E-core value. I'm going to just draw it straight across. So I'm going to grab this point and try to get a nice straight line here. And here I have my line that's related to my E-core value. Now I'm going to take another line, and I'm going to start from the cathodic branch down here. I'm going to say this is my linear region. You know, it looks like a straight line, and I'm going to draw it straight through the E-core value. So let's start about right here. Stay with the linear region. I'm going to come right there and cross over. That looks pretty good. And one thing I'm going to note is, well, I'll come to the slopes here in a second. So here's the extrapolated line for the cathodic branch. Now I'm going to do the same thing for the anodic branch, but instead of starting into what I can see as the linear region, or I think might be the linear region, I'm going to start from the origin right here, this crossover point, and I'm going to find a line that's tangential to the data that I have right there. And hopefully I'm going to be able to get a good fit here. So this is pretty close to being tangential to the data. Let's go ahead and put it right there. And those are going to be the three lines that I have. And if let me go ahead and back out of this and zoom in again. No, I got a little bit too close. One more time. Okay, that's a little bit better. So you can just see the tip of the line that I made right here. Actually, let me make this a little bit longer here for us. It's fine. What the point I wanted to make is that if you try to find the linear region here in the anodic branch, it's difficult. I could have maybe came and thought this was the linear region or somewhere over here, and the slope of that line, which is what we're looking for, the slope of those lines I drew are the Tafel constants, it would be off, because based on what we looked at from this plot, we should have both of these extrapolated lines cross over at our E-core, and they should fall right on I-core. All this goes back to the beginning when we talked about the mixed potential theory, and that the rate of the anodic branch has to be equal to the rate of the cathodic branch, and they're all going to be meeting right at I-core. So it's just coming back to the theory involved with using this technique. So going back to our data that we're taking a look at, the two things I can do are take a look at these two lines. So for the cathodic branch right here, I have a slope of about 173, it says. So let's go ahead and just put that in here. We're at 173. We'll take a look and compare these here in a moment. Just the end here is the tip of my anodic branch, and that slopes just about at 51. Let's come back here. We're going to be at 51. And then at this crossover point, I'm going to zoom in really close to this. Oh, I'm drawing lines. Sorry. Let's get rid of that line. I did it again. This is what I want to take a look at, where we're crossing over here. So if I draw one more line and come straight down from here, where I'm meeting, except the line, this point right here is I-core, and it's off a little bit. It's not exactly straight, but this is what we're looking at for I-core. This is a log plot of the current we're looking at. So here's 100 microamps, 200 microamps, we got 300 microamps, and so we're going to say that we're right about, let's see, that would be 2, 3, 4. Let's say 203, about 340 microamps. Any objections to that value? I'm just kind of eyeballing it here. So I-core, I have about 340 microamps. And so if we compare what we got here from the fit that we used fitting the Butler-Vollmer equation through the software, you can say it's very close to what we're going to get for a fit here, just using the graphical method and lining all our lines up correctly. So for the anodic slope, graphically I got about 51, got about 62 here for the fit. For the cathodic slope, I have about 173. Here I'm about 178. I-core I have at 340. Over here I'm at 356. Corrosion rates about 157 millinches per year. Here I'm closer to about 130. So the two line up pretty well. I'm happy with those results. I think if I spent a little bit more time really close to the data, I could probably get all those values to line up almost the same. But that gives you a basic idea of how we're coming up with the values of the two Tafel constants. And again, this is a easy enough way to come up with the corrosion rate, which is what we were doing with LPR anyways. But now we can do it much faster. Since we have these two constants, we can run a quicker experiment that's non-destructive and reach this I-core value. And we do that using the Stern-Geary equation that I mentioned before. And once you have I-core, you can then calculate a corrosion rate. Let's see how our data is looking. We are almost done here. So this is the live data I'm actually collecting right now. If you'd like to see it, I can turn on my camera and you can see what I have running here. Let's see, I think this is going to bring up the camera. I think everybody can see the camera now. So here I have my cell. It's the paint test cell. It's the same cell I used last time, and if anybody likes, I can kind of walk through how I set it up. I don't want to touch anything until it's done performing the experiment. If you look really closely, you can see the counter electrode in there. And yeah, a big bubble just popped up right there. So we're getting far away from the open circuit potential. We have reactions taking place on both the surface of our sample and on the graphite. So again, this is a technique that's far away from open circuit. It's a very active experiment. You will modify the surface of your sample, especially if you run a full potentiodynamic scan and you're getting, like I said, a 3-volt sweep. Yeah, I'm not sure if anybody could see it that well, but you can see little bubbles are slowly rising up on there. It's not just a fuzz in the video. You're actually observing it right there. Using the Gamry interface 1010 potentiostat, I have a graphite rod as my counter electrode that you can see the red cable here. Right here you can see the cable for our reference electrode, and then here are the two connections, working and working sense that are connected to our metal sample. And you can see that I'm using a sample mask right there, that yellow piece. And it's about a centimeter squared exposed there on the surface. I talked a lot about the cell setup last time in the polarization resistance experiment. So if you want to go back and watch that webinar, we discussed a little bit more. And in general, if you're looking at cell setup stuff, I did a webinar a month or so back talking about all the different cells that we have and how you can set those up. So any questions about those, I'd encourage you to go watch those two webinars, and you can get some useful information there.
Hey, Andrew, can you pause for a second?
Yes.
Is this camera mobile? Can you zoom into that cell just a little bit?
I can just pick it up and move it. So let me see
Okay.
if I know. Hopefully nobody gets dizzy from me doing this. Avert your eyes from the screen for a moment. Let's see. Okay. Well, there you can certainly see the bubbles that have formed on the counter electrode. And I'm going to move this up, and you can see the surface of the metal sample. Ooh, it's hard to see it from there.
It's a little harder with
The curvature of the glass makes it difficult. I think well, take my word, you can see bubbles on the surface of the metal sample as well. Excuse me a second while I try to get this thing put back. Computer. I guess I can take a second. Here's the paint test cell that I'm referring to, and the surface is what you'll see. This is what I was trying to show you. This is a sample that I ran previously. It's awfully bright. Let me get rid of this. Let me try to get it at a good angle. There we can see corrosion certainly happened on the surface here of this guy. That looks like a good angle right there. This is the O-ring that holds it intact. This is just an open cylinder. So this is our working electrode that's exposed right down there, and then I connect the cables to the end of the metal right here, and then have the counter and reference electrode here to complete the circuit. So that's the cell I've been using for the last two webinars. Very simple, very easy to use. Unfortunately, you have to have a large enough sample to fit underneath the cylinder, and you have to, and it has to be flat. But if you have different sample geometries, we have ways to support those. So just give us a call, let us know what you have. We'll see if we have something out of the box. If not, we can talk about ways that you can get your sample in there. You can still run the same experiment. The one key though is knowing what the surface area is on your sample. That's something you're going to have to know to run these experiments. Let me go back to sharing the screen here. And maybe we have finished the experiment. I know we're going to be awfully close. And we have. Here is our curve right here. This is the data that we just collected in the cell I just showed you. I know the experiment's done because it's let me know it's completed right there. So what I'm going to do is I'm going to get out of framework here. And luckily we had a good experiment. I don't need to use the data that I collected yesterday, which is this right here, just in case you know, the experiment didn't want to perform. It was gun shy for the camera. I ran this experiment yesterday, and as you can see, still very good fit. Let's go ahead and open up the data we just created, and let's see what we have. So here's the data that we just collected. Again, we have a fairly linear region right here for the cathodic branch. Our value of E-core, which is going to be close to this 498 that we see right here, that's pretty good. It is very close to what our observed open circuit potential was. Don't think that this was an unstable open circuit potential. This is from 505.6 millivolts to 505.6 millivolts. So our scaling probably needs to be a little bit better, but it's very stable. We're right there at 505 millivolts. So we have good data here. That's one thing you want to check. You want to make sure that this value that you observe of what E-core is going to be is pretty close to what your open circuit was. You don't want those two being too far apart. It'll affect the fit that you will use with the software. If your open circuit potential is far from your E-core value, then weird things can happen with that fit. So that's one pass-fail test to look at your data with. Let's go ahead and fit the data. First, let's do it with our software. So again, I'm going to pick a certain portion of the curve here. Let's take this data about right here, and we're going to fit this data right here with the Tafel fit that we just used before. Go ahead and let it calculate those values for us. And let's see what we got. Let's copy these into Excel so we can see them a little bit better. Okay, so we have an anodic slope at about 39, well, 40 millivolts per decade. The cathodic slope's about 140 millivolts per decade. This is our I-core value, about 20 microamps. E-core value is right there at 500 millivolts. Gives us a corrosion rate of about 8.8 milliinches per year. Let's see what the graphical fit tells us on that. So I'm going to get rid of this fit that we just put on there so we can just see our data again. And first thing I'm going to do is I'm going to draw a line right through here. Like that. Now I'm going to do the cathodic side here, and there's a little bit of curvature right there. So that could affect us a bit, but I'm going to call this right here our linear region. Not so much where it's crossing over in here, but kind of using this as a more linear region as opposed to the curvature you can see forming right there. So let's draw this line. Like I said, I'm going to take it from about we'll see how good that fit is. Actually, I'm going to redraw that line.
We have a question from somebody then, if
okay,
when you're ready.
Whenever you're ready, go ahead.
Okay, let me unmute Wogan.
Oh, sorry, I didn't realize it was going to be across the whole thing. I was just wondering, is this is getting a Tafel curve a good fit for something with like a chemical film on it, or is it more for pure metals?
Well, you mentioned chemical film. That could be a lot of different things. I will say that I had a backup solution in case the sulfuric acid that I'm using on this steel was going to be too aggressive and not give me a stable open circuit. So I had a corrosion inhibitor that I was going to add. So there's a lot of different corrosion inhibitors, but one certainly will form essentially a film, a barrier of sorts on the surface. So yeah, there's no reason that you can't use it. I can't say for sure it's going to work all the way across the board. You'll just have to give it a shot to begin with. But one good thing, if we are talking about, at least in the sense of corrosion inhibitors, is that you have bare metal, and you want to see how well your corrosion inhibitor performs. You run this experiment on the bare metal, and then you add your corrosion inhibitor and see if your corrosion rate goes down significantly. So yes, you certainly can. It's been done, and you can try it. There's no reason it shouldn't work. But in terms of, well, are you using the film for corrosion protection, or are you trying to get other information from the film? Would probably be the question for Hogan. So that would be one thing just to think about, is what you're trying to get, what kind of information you're looking for. So if it's a coating that we're talking about, I doubt you can run this experiment, because you're not going to see any corrosion from a coating until the coating starts to fail. So this experiment and using the mixed potential theory that we're talking about to get you Butler-Vollmer and I-core, none of that's going to be valid. But if we're talking about some kind of a thin film that's still letting electrolyte pass through, and then yes, it's very possible, I'll say. But back to our graph to see if our data works out well. So here's my cathodic slope, which I still think I could probably draw a little bit better, but we'll go with it. Let's see what we end up with. Probably shouldn't be too far off. Like I said before, I'm going to take a line from the origin. I'm going to get this a little bit zoomed in. Because I have a feeling, yeah, maybe that's too close. That's a little bit closer, that's better. So I want to draw a line where I'm crossing over E-core and our extrapolation from the cathodic side. And this is where you're going to get a little bit of variation, because if I was to take the data that I have fairly close to the open circuit, then my crossover point is going to be closer to this region. But then I'm cutting all the way through the data. It's no longer tangential. If I come down here a little bit more, then I'm getting tangential with the data and not crossing over any of it. So this is where you know, you have to use experience and just run lots of tests to try to converge on a value. So I'm going to run it up right here. I'm going to say that's going to be our value. And then I'm going to draw one more line that's going to add up to what I see for my I-core value. It should be pretty close. Okay, so let's look at the slope values that we got. For our slope here, for our cathodic side, I have about 136, 137 millivolts. Let's go ahead and plug that in. For the anodic side, I just hover over it. And what I'm doing, I'm hovering over the lines, and you see a little box pops up, and it tells me what the slope of that line is. So the slope of the anodic side, oops, got off the line, is about 31 millivolts per decade. Our I-core value, where am I? Here I am, is going to be, oh, our fit is off when it comes to this, because I'm at 10, 20, I have my fit, it's getting close to 20 microamps. That's off of what we had from the other value, isn't it? Oh, no, it's not. For some reason, I thought I saw a few hundred. Okay, so here we go. We have our fit from the software fitting to Butler-Vollmer. We have a beta value of 39 millivolts. Cathodic beta value about 140. I-core is 19. Our E-core is at about 500, 499, negative 499. Corrosion rate comes to close to about 9 milliinches per year. So graphically, our anodic slope is at 31, pretty close to 38 here. Our cathodic slope's at 137, awfully close to 141. Our I-core value, I called it right at 20, and it was a little short of the line, so 19 was probably a better estimate. Either way, our corrosion rate is awfully close. 9 here, I have 8.7 on this side. So I say we did a pretty good job fitting our data. And that's how you find your Tafel constants, just that simple. Still, the key to the whole thing is first getting good data, and that can be difficult. So once you have good data and you can realize that you have good data, then the fits aren't nearly as difficult as they may seem. But trying to fit this to bad data will be difficult, as in anything, trying to use bad data for something. But yeah, I guess we can talk about questions people have with regards to fitting this data if you like. You guys have questions?
Okay. Yeah. So we have a couple questions here. I do want to say that that's a really nice comparison between an actual fit and then doing it manually. That's a nice way to show that.
Yep.
Anyway, somebody asked if, typically when we think about 2 weeks ago, doing LPR is a non-destructive technique, but a TOEFL is a destructive technique. Are there methods you can use to determine if a sample has been altered by running a TOEFL, or just assume that it's been altered since you ran a TOEFL?
Well, you can. I mean, yeah, there's methods to it. If we think back to a previous question, maybe a better way to look at it is somebody was asking the order to run experiments in, and they were saying, we can first run impedance because that's going to be non-destructive, and then LPR after that. I would point in that direction. If you want to use the same samples over again, then use what is considered a non-destructive technique first, and then something else. But in terms of whether or not this sample has undergone a change, whether you did it through an experiment or not, is going to be, I mean, there's a slew of different ways you can do it. Visually, once I finish with this sample, even though I'm going to drain it and rinse it out, in about an hour or so, I'm going to see rust forming on the surface. So that's almost impossible not to get around. You're visually going to see something on the surface. If you can't observe the surface, then you can start looking at things electrochemically, and that would be you can run any number of different experiments. Actually, you can just observe your OCP value over a given amount of time, see how that's changed. You can run impedance on it and probably pull out parameters there and see how those have changed. You could do the same with our LPR experiment and see what changes have happened on the surface. So yeah, there's a slew of different ways to look at that. But if the underlying question really is if there's an order that we want to do this in, then do non-destructive first. But and honestly, with these kind of experiments, you want to run as many of these as you possibly can. So have lots of samples, run lots of experiments, and if you want, go back and run the same samples over again. But just be wary that you might have rust on the surface, and that's going to affect the results you get. Also, be very wary of what your material actually is. When we go back and we look at this mixed potential theory right here, this is assuming that these are the only two reactions that are taking place. The only metal on the surface is zinc. But what if you have some kind of alloy, and you have zinc, you have steel, you have titanium, you have all kinds of different materials on the surface? All of those are contributing to what this I-core value is. And you can look up information on how you use the mixed potential theory on any number of different constituents that are in the material, but be wary of that. I think I talked about it with the PolRes demonstration, but whatever corrosion rate you come up with, it's a mixture of all those different materials, or one of those materials is absolutely dominating the rest. So be wary of that stuff. I think I kind of went off on a tangent with the question, but still just thinking about helpful things that people can consider when doing this. But,
okay, let me make there's a couple of questions related to electrolytes, so let's do easy ones. Okay. One is, what electrolyte did you use today? And then the second one is, what happens if you're in a resistive electrolyte? Is there a way to say correct for that with IR compensation or?
Yeah, you can exactly do that. Well, in terms of the first one, I used about 0.1 molar sulfuric acid. For the second one, there is an application note on our website. I believe it's called galvanic corrosion. And if you scroll through that towards the bottom, we talk about exactly that question, and that's using IR compensation in these experiments. So yes, you certainly can do that if you're in a resistive media that you have substantial IR loss. So yes, you certainly can do it. Be wary of using it. Make sure you absolutely need it if you're going to use it. But that application note certainly has. Correct me if I'm wrong. I believe it's called galvanic corrosion for that application note. It's certainly in our corrosion part.
We do have another one also on understanding IR compensation. I posted a link in the chat box for everybody.
Yeah, that one as well. Yes. So yes, certainly can use IR compensation. Just review what it is first so you understand what you're doing.
Okay. Andrew, there was a couple questions here. Can you quick show how to do the fit, the built-in fitting method?
Yep. Let me get rid of all these lines. So for our software, if I was just to go here and tell it to fit, it's going to prompt me to select a portion of the curve to use. So that's the first thing you have to do with almost all of our fitting software. Is first you have to select a portion of the curve. And as you move around down here, it's going to tell you what these icons are, what they're for. Here is select portion of curve using the mouse. This is the one I like to use, so I must use it exclusively. So I'm going to click on that, and then I'm going to select the two regions or the region of the data that I want. So I'm going to pick a point here, and then every data point from here all the way across is going to be included. So I'm going to pick from there, and let's go to there. So this is the data that's being selected, and then I'm going to go down here for the Tafel fit. So for the fit that we're using, the regression, you can pick the number of iterations. You can, if you want to pick out your own values to start with, you can by using the seed value. And then the weighting down here, you have a log weight, linear, or an average. So since we're on a log scale here on the x-axis, then I would use the log weight because if you use something that's linear, then these large values are going to dominate because these values are just smaller. They're not going to affect what the fit is nearly as much. Same thing for the average. The average and the linear are somewhat similar that way. I would stick with log fit until you feel the need that you might need to try something different. And that's going to be getting into when the data isn't quite as nice as you would like it to be. But let's just stick with log for the time being, because that's going to be a better average of everything, given that you're using a log fit. These larger values aren't going to dominate the fit. The smaller values here that are orders of magnitude smaller are going to have just as much as an effect on the fit as these larger values are. So once we have our setup screen here, we pick what we're going to use. We just hit calculate. You close this, and this little tab just showed up. Now I already did a fit for it earlier, so so it was already there. But prior to doing any fit, this tab would not be there. Once I do that Tafel fit, you get a new tab, and this tab is going to give you what these values are. It's also going to give you the one thing I didn't throw up is essentially the goodness of fit, your chi-squared value right here. But it gives you all the values right here, the same ones that I plugged into Excel here, a little bit larger, easy for you to see, to use for the comparison. But that's how you make your fit, just as simple as that. Be wary of the data points that you choose. Once you start choosing different data points, the fit's going to change a little bit. But you know, that's something to just takes with experience, fitting a lot of different data. But when you use this fit, go back and graphically fit it. See if the two line up. Don't trust a regression just because it's easy. Back it up with another technique. You have two techniques that are converging on the same value. That's far more powerful and more reliable than just using a fit and saying, well, that must be it because that's what the software told me. But that's how you do it. Simple as that.
Okay, thank you. One moment, Andrew.
Yep. I just thought of something else that when I was doing this was somewhat interesting. If we go back to this potentiodynamic scan, I'm going to take this off of the log scale on the x-axis here. And this is what we end up with is this curve. So this region right here is our Tafel region, but we're no longer on a log plot. And if you zoom in very, very closely, and you keep zooming in, you see our region right here. Remember, if I go back to our open circuit voltage for this measurement, and this is from the file that I previously connected from Penn State, and we're sitting, you know, about 510 millivolts. If you go to about 510 millivolts here, then you have this little linear region. This is where you get your polarization resistance data from. That's the PolRes graph that we produce. Oh, I did it again. That's where we produce that polarization resistance graph. There you go. That looks like a nice straight line right there. So just something to relate what you're doing in the different techniques. It's you know, they're all connected. We're not doing something completely different. We're just perturbing the system further. But yes, were there any other questions?
Yeah, there's a lot more, but I know we're running out of time. But I'm just requesting everybody that submitted a question to please make sure that we have your email address so that if we don't get to it, we can follow up separately with each of you.
Yeah, if you guys have very specific questions on your systems, then yeah, share your email with us and we can discuss what's going on. But those require a lot of conversation. We need a lot of details that we can't go through the webinar, certainly for every person. So if you want to give us your email address, if you just want to send us an email through our website, it's easy enough to do, and we can see what's going on, see if we can help.
Jacob or David, do you have any that are general enough that can be asked for everybody?
I do not.
I do not either.
Okay. Just 1 second. I'm still scrolling through a bunch of these.
Did any of the questions generate what our next webinar is going to be? It happened last time. It makes life simple when you guys give us the ideas like that. And
discuss ZRA next time.
Okay. That's going to be a really boring webinar in terms of what we're going to observe. But it can be interesting. Well, something Jacob mentioned before is electrochemical frequency modulation, EFM, as possibly potential. So if anybody would like to hear about that, send us an email and tell us. If you guys submit enough stuff, we can run webinars on what's interesting to you as opposed to us thinking of what might be interesting to you. We're always open to submissions or suggestions as to what we should be covering in these things.
Okay. Yeah, I think we're gonna pause there because we do have a bunch of specific questions, and I have everybody's email address. Make sure David and Jacob to save the chat so we have whatever questions have been asked to you. But let's stop there, and we'll sort of wrap it up. I want to thank everybody for joining us. Thank you, Andrew, for putting this on. That was a really nice demonstration between automatic fitting and then doing it manually too. And just a reminder to everybody, we have recorded this, and we're going to send a link out with tomorrow's Friday Focus email so that you'll be able to go back and reference it again if you need to, or pass it on to your lab mates. And then keep an eye out for when we announce our next webinar. Please remember to register, and we hope to see you there. So thank you for your time, everybody. Have a nice weekend.